Ever wonder what's actually going on inside your phone, your computer, or I don't know, even your coffee maker? Well, it all boils down to three surprisingly simple ideas. In this explainer, we're going to pull back the curtain on the magic behind pretty much every electronic device you've ever touched. Let's get into it. So you look at a circuit board like this, right? It's like a tiny city, just a maze of components and connections. It looks impossibly complicated, like it's written in some secret code. But what if I told you this entire world is built on just three basic concepts? Seriously. By the time we're done here, you'll start seeing the simple patterns inside all this chaos. So where do we even start with this whole thing? Well, it all begins with potential. Think of it like stored up energy, an unseen force that's just waiting for a reason to get moving. In electronics, this potential is the push that gets the entire show on the road. And this is a fantastic way to picture that push. Imagine an invisible hill. At the very top, you got a ton of potential energy, and at the bottom, you have very little. That difference in height, that slope, that is what we call voltage. It's the potential for something to start rolling downhill all on its own. Okay, so we've got this invisible hill, this potential for things to move. But, what if we don't want everything to roll down all at once? What if we want to, say, collect a bunch of stuff at the top of the hill and then decide exactly when to let it go? That's where our very first component comes into play. The answer is a capacitor. A capacitor is basically a tiny bucket. Its whole job is to store up electric charge. It's like a small dam holding back water, building up that energy until the moment is right to release it. And how it works is, honestly, beautiful in its simplicity. You just have two metal plates, really, really close to each other, but not touching. When you hook up a battery, positive charge piles up on one plate and negative charge piles up on the other. That separation creates an intense electric field between them, storing energy almost like a tightly wound spring. And here's where that simple idea hits the real world. You've probably seen these things before. If you've ever taken apart an old gadget, they come in all shapes and sizes. Little ceramic discs, bigger cylinders. They might look different on the outside, but on the inside, they're all doing that exact same job, acting as tiny reservoirs of charge. Now, when engineers are designing this stuff, they don't draw a little picture of a can, right? They use a special language, a shorthand. And the symbol for a capacitor makes perfect sense. See? It's literally two parallel lines, just like the two plates in the concept. It's a universal sign that means, hey, store energy right here. All right, so we have the potential, the push from the hill. We have the capacitor, our reservoir for storing it up. But all that stored energy is pretty useless if it just sits there. So now it's time to open the floodgates and let it flow. And that flow of charge is what we call current. It's not just about how much charge there is, it's about how fast it's moving past any given point. Think of a river. The current is how quickly the water is flowing. We measure this rate in amps or amps. More amps means a stronger, faster flow. But here's the thing. A river without any banks is just a flood. An uncontrolled flow of energy is just chaos. A spark, and then it's gone. To build anything useful at all, we need the third and final piece of the puzzle, control. We need a way to tame that current. And that control has a name, resistance. A resistor is basically a bottleneck. It's like a faucet in our electrical river. The charge flows easily through the wire, but when it hits the resistor, it gets squeezed and slowed right down. A resistor is how we tell the current exactly how much we want it to flow and where. And this is where it all clicks into place. These three big ideas, the push of voltage, the flow of current, and the control of resistance, they're all tied together by one single beautiful equation, Ohm's law. V equals I times R. This is it. This is the simple rule that governs the entire world of electronics. It's the master key that unlocks everything. So now we have our three basic building blocks, voltage, current, and resistance. You can really think of them as the Legos of electronics. So let's see what happens when we start snapping them together. There are really two basic ways to connect our Legos. You can put them in series, which is like linking them end to end in a chain, or you can put them in parallel, which is like giving the current multiple paths to take, side by side. But here's where it gets a little weird. Resistors and capacitors behave in completely opposite ways. You put resistors in a chain, in series, and their resistance just adds up. Simple. But with capacitors, it's when you put them in parallel that their storage capacity adds up. Kind of funny, right? All right, time for a little pop quiz. Let's put this into practice. Now, this circuit looks like a bit of a tangled mess, I know, but we actually have all the tools we need to solve it. Our job is to figure out the total capacitance of this whole network. You ready? Let's break it down together. Okay, first things first, let's hunt for any simple connections. See that 20 and that 5? They're in series, one after the other. So we use our series formula, and poof, they become a single 4 microfarad capacitor. Okay, our circuit just got simpler. Now look, that new 4 is in parallel with the 6 and the other 20. And for parallel, we just add them up. That gives us 30. We're almost there. Now we just have 2 left, our 30 and the 60. And they're in series. So one last calculation, and boom, 20 microfarads. That's it. We just took that complicated-looking web, and by applying our simple rules one step at a time, we boiled it all down to a single number. That is the power you have when you understand the basic building blocks. And there you have it. Potential, storage, and control. From the simple push of voltage, the patient energy hoarding of a capacitor, and the precise throttling of a resistor, we can literally build our entire modern world. From your smartwatch to satellites in orbit, it all comes down to those 3 ideas. So the next time you flip a light switch or tap on your phone screen, maybe you'll picture that invisible world of hills and dams and faucets all working together perfectly. Makes you wonder, what else is hiding in plain sight?